In many applications of graph theory, a very common thing that we care about is actually something called an edge weight, where some edges, there's some number that corresponds to the edge that's significant in the application. So these numbers that are attached to the edges, they're called edge weights. Okay, it can represent all kinds of things. Here's an example where it represents the cost of flying between two cities. Okay, so we've got the cities LA, Seattle, Dallas, Atlanta, and Chicago. And we see that the edges connecting them have weights, edge weights. Those are the cost. So the cost to fly from Atlanta to Dallas is $85, and so on. So, how many vertices and edges does the graph have? Well, looking at this, we've got 5 different cities, and those are the vertices. So 5 vertices. Okay. For edges, we need to count all the different connections. Okay. Well, we can go through and count. We say, well, I've got from Chicago, I've got 1, 2, 3, 4, right? And then from Atlanta, I've also got 4, Dallas. So each of these has 4 connections, which would be a total of 20, except we'd be double counting each of those. So if you go through and count these, you actually find that there are 10 edges depicted here. Is the graph connected? In other words, is there always a way to get from one city to another? And that is certainly the case here. This is a fully connected graph because it's always possible to get from any city to any other city in one go. Okay, what is the degree of the vertex representing Los Angeles? Well, looking at Los Angeles, we see that we've got a connection there, 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 and there. That's 4 edges connecting to Los Angeles, so the degree of LA is 4. If you fly from Seattle to Dallas to Atlanta, is that a path or a circuit? Well, a circuit has to start and end at the same place. And if we go from Seattle to Dallas to Atlanta, we did not end where we started, so it's certainly not a circuit. But it is, of course, a path because we went from Seattle and then connected to 2 other places. So this is a path. And finally, if you fly from Los Angeles to Chicago to Dallas, then back to Los Angeles. Well, we started and ended in the same place. That's not just a path, that is a circuit. Okay. Now, of course, every circuit is a path. But if it's a circuit, we want to indicate that it is because that's a much more powerful way to classify it. A special type of circuit or path is called a Hamiltonian path or Hamiltonian circuit. If you have a circuit that's a Hamiltonian circuit, that means that it visits every vertex in the graph exactly once with no repeats. Okay, so this is where we go to every vertex, but we're not coming back to a vertex, and we're just making sure that we've visited every single vertex. So, because it's a circuit, we'll start and end at the same place, okay? But we're not going to like pass through a vertex and then, and then come back again. A Hamiltonian path will visit every vertex, but we don't need to end where we started. Okay. Now, a problem that is common in graph theory is called the traveling salesman problem, and it's simply the problem of finding a path that visits every vertex without returning to anyone. Okay, this is the traveling salesman problem because a salesman would want to travel and visit multiple people, but of course not go back. And so they would want the most efficient way of visiting every potential buyer without going back. So here's an example. Find a Hamiltonian path in the graph below. Then, if possible, find a Hamiltonian circuit. So for a Hamiltonian path, we just need to start somewhere. And the nice thing is if there is a Hamiltonian circuit, it doesn't matter where you start, because it's a circuit, it needs to come back to where it started and needs to visit everything. So I'm going to go ahead and just start down here at vertex B. All right, and we can just gotta start moving and visiting every every vertex. So let's go ahead and start going through. And it's not really super difficult to find these usually, but usually you'll find that there's a problem that arises. Okay, right here you see, okay, well I can come back down to E. Notice I've now visited every vertex. Okay, so I have found a Hamiltonian path. Hamiltonian path. Question is, can we find a Hamiltonian circuit? Now at this point, it should be clear that what we've drawn so far cannot be part of a circuit, because to get out of E, there's only one direction that I can go, and that would be up to C, and I'm not allowed to revisit that vertex. So what I've drawn here cannot be converted into a Hamiltonian circuit. Now I'm going to show you a technique to work with when you're trying to find Hamiltonian circuits. And this doesn't work for everything. Well, it's something that works sometimes, just depending on your graph. What we're going to look at is simply any vertex that has a degree of 2. We know that we're going to have to use both the edges in a circuit, because we have to come in to the vertex. So like, for example, this H. I have to come into H, and I need to leave it. So I need to use both of those paths. Okay? Same thing for, so every vertex of degree 2. So that's this A has degree 2, so I'd have to use both of those. B has vertex 2, so I'd have to use both of those. And right there, we know that we have a problem. Because notice that we've now visited C multiple times. Okay, we've visited this vertex, we've come and left, but we've also came in another time. So immediately we know there is no Hamiltonian circuit. Okay, so that's a nice technique that we can try when you've got some vertices of degree 2. And sometimes you'll see that when you include each of those edges on the degree 2 vertices, you run into a problem where you have visited a vertex more than once. Okay, for a Hamiltonian circuit, you'll just need to remember, if a vertex ever has 3 connections to it, that's going to be a problem. All right, so that's what you're kind of looking for when you go through and make those connections. Let's try this one here. Find a Hamiltonian path in the graph below. Again, Hamiltonian paths are usually pretty straightforward to find, but not always. I'm going to actually start with the Hamiltonian circuit, because we have a very clear technique for finding that. So everything with a degree 2, I'm going to go ahead and circle them. That's degree 2, that's degree 2, that's degree 2, and that's degree 2. Those are my degree 2 vertices. We have to include both edges for each of those degree 2 vertices. Okay. Now, if we have a Hamiltonian circuit, we would need to be able to connect the ends, connect this all into a single circuit. Now I've got an end right here at H and an end right here at B. And the only vertex I haven't visited so far is D. And I see I can get there from H. The problem is there's no way to connect from B to D without going through a vertex that's already been visited. So there is no Hamiltonian circuit for this graph. Now, on the question of whether there is a Hamiltonian path, you'll notice that what we've drawn here actually is a Hamiltonian path. We have visited every vertex and had no repeats. Okay, and that's all that's required for a Hamiltonian path. Okay, notice that same technique actually worked out for us. We know that for a Hamiltonian path, every vertex that has a degree 2, we have to include both edges that connect to it. So you use those connections, and then from there you can figure out if you can create a Hamiltonian path. So what's drawn here is a Hamiltonian path, but there is no Hamiltonian circuit in this graph. This one here is fun. Let's go ahead and do the same thing here. We want to start with any vertex that has degree 2. So I have 4 of them, just these corner pieces here. Those are the vertices that have degree 2. That means that I have to include both edges for each of those vertices. Now that shows we're pretty much stuck here. There's only 2 vertices we haven't connected here. So if I come down, I'll just come down from this one here. If I come down and visit that, then I've got to move over to connect that. And now I see, well, I've got to connect everything through. And if I just connect this down and connect this over, there I see both a Hamiltonian path and, of course, a Hamiltonian circuit. So this, what's drawn is both a Hamiltonian path and Hamiltonian circuit.